All right, so thank you everyone. Sorry for the slight delay. Today, I have the pleasure of introducing our speaker today, Claire Cohalan. Claire is a graduate of the MPU program. You did your master's here right before I did, actually. And you have been working as a nuclear medicine physicist at the SHUM since 2015. And she's here today to talk to us about Theranostics. So please take it away.
I could remove my
Yes.
All right. Hi, everyone. So I'm Claire. I'm a clinical physicist in nuclear medicine at the SHUM, which I think is a super exciting position, but there's not many of those positions in Quebec. And so I'm using this seminar to kind of do a pitch that there should be more of us in Quebec, because nuclear medicine is actually huge in Quebec. Proportionally to other provinces, we've got a lot more here than elsewhere. And I think physicists need to be in this field and need to be working on this and advancing this field at a faster rate than it's going. So that's my pitch. Those are my disclosures for this talk. So I'm going to talk, about, inverse screens. So I'm going to talk about treatments in nuclear medicine specifically today. So we know that nuclear medicine is mostly diagnostic, and it has been for a long time, but we have had treatments in nuclear medicine for a long time, and that field, that subfield of nuclear medicine is really exploding right now, and so that's what I wanted to talk about today. So to put it on the map, we've got already an arsenal against cancer, so how to treat cancers in hospitals. So there's surgery, of course, but then there's external radiotherapy, right? And you guys are all pretty familiar with that. So we're treating primary sites with radiation. So trying to give as much radiation to the primary site while sparing other tissues that might be around that site. And that often goes hand in hand with chemotherapy. Chemotherapy is another way of treating cancers, and it's completely different, right? You're using more chemistry and more biology to go target specific cells, no matter where they are in the body. So again, external radiotherapy, you're targeting primary sites. Chemotherapy, you're going to get these external cells, no matter where they are in the body, whether they're in the primary site or externally, and chemically, you're going to go target those cells and try to kill them as well. So they're quite complementary, and targeted radionuclide therapy is actually a bit of a mix of both, right? You're going to use pharmaceuticals, so it could be the same pharmaceuticals as in chemotherapy, but you just make them radioactive so that they deliver a dose to those problematic cells in the body instead of killing them in a more chemical way. So you're going to target specific cells in the body and the immediate neighbors of those cells, depending on the type of radiation that you're using. So just, targeted radionuclide therapy could just be a tool. It's an additional tool in our arsenal that could be done in conjunction with external radiotherapy, in conjunction with chemo, or on its own, depending on the type of cancer that we're trying to treat and things like that. So a nice little pictogram that I like about to kind of illustrate this. You got external beam therapy, where you're trying to give radiation to a specific outlined field, as primary site, which again you can outline and calculate. And targeted radionuclide therapy is more like chemotherapy. You're going to give radiation dose that can be distributed through the body. So again, it can be distributed into a primary site mostly, but the particularly nice thing about it is that it can also target cells that might not even have been picked up yet as cancerous sites in the body. So you can even go attack those cells before they're even diagnosed or that show up on a scan, which is why it might be a good complementary tool for things like external beam, right? Like chemotherapy is, to make sure you go get the whole malignancies. So just a brief history of this. Again, we've been doing treatments in nuclear medicine for a long time. We've been doing it since the 40s, administering radiopharmaceuticals to treat. And for all of these decades, it's mostly been fixed activity that has been given, or an activity that's proportional to the weight of the patient. So it was quite crude over the years, which was fine. It still served its purpose. But what I'll be talking about later is trying to push it a bit forward and make it a little more quantitative. We've also developed models over the years to try to calculate the dose to the different organs or to the different sites in the body. A lot of these were based on MIRD or the MERD standard bodies that have also evolved and gotten more complex over the years. So, there's a long history of evolution of these calculations. But a lot of those MERD, like standard body, standard patients, are much better when it comes to calculating the dose to different organs for example, nuclear energy workers. So you've got nuclear energy workers who, for example, will inhale, say, americium. The americium will go through the lungs and then will make it through the stomach and out the rectum. And you can use these models, these standard models, to predict the dose to the different organs for these, say 50 workers that were exposed to that americium. However, when you're trying to do patient-specific calculations, those standard humans don't have a tumor that's soaking up the radiopharmaceutical, right? So they do full organ doses, but if you've got a tumor that's either in one part of the liver or an external tumor that's close to another tissue, this system kind of breaks down, right? It can't account for those patient-specific anatomies of the tumors. So just to quickly go over what has been done forever, thyroid therapy is one. So iodine in its kind of more ground state or natural state goes to the thyroid. So whether you just have a hyperactive thyroid, or if you've got a thyroid cancer, you can give different amounts of activity of iodine, and that will naturally be soaked up more in the thyroid than elsewhere in the body. If you've got metastatic thyroid cancer, so thyroid cells that are cancerous that have gone elsewhere, they too will take up the iodine. So you can go treat those metastatic sites with simple variants of iodine. So we've been doing this for decades and decades, typically on a fixed activity basis, although there has been, I'm getting feedback all of a sudden.
All right, I'll try to push forward.
Yeah, so we've been doing, no, this, I don't know how to change it. Oh, I can mute this one. Ah, better. You guys can still hear me? Tanner, give me a thumbs up if you can still hear me. All right. Which must mean that this mic just started working. Anyway, okay, so fixed activity, we can do some dosimetry, but it hasn't been that well, standardized, say. We've been also doing bone pain management treatments for a long time with radiopharmaceuticals. So we know, for example, that calcium is a bone seeker. So things that look like calcium, so anything in the same column as calcium in the periodic table would also chemically tend to go to the bone. So if you use strontium 89, for example, which is a beta emitter, or radium 223, which is an alpha emitter, that tends to, in a simple state, that'll tend to go, get soaked up by the bone. And so often when people have metastases that go in the bone, that can be quite painful. You can try to reduce the size of that tumor by irradiating it with things like radium 223. So at the SHIP, we've been doing it for a very long time. And again, it's not overly, we don't make it a complicated treatment. We give a specific dose. It comes in a little tablet that's the same for every patient. And we administer that for bone pain management. There's not much dosimetry or quantification that's done, but it works. And when we're talking about bone pain management, we're talking about palliative care. So as long as it's working and the pain is going down, we tend to be happy with that. So those are examples of treatments that we've been doing for a long time with radionuclides in nuclear medicine. But in both of these cases that I discussed, we're talking about very simple molecules, right? We're basically giving radioactive salts to our patient and just using the natural chemistry of that radionuclide to go find the problematic site in the body, which is fine. But can we do more? And the answer is yes. Obviously, we're now doing a lot more than that. So what can we tag as radiopharmaceuticals? What kind of pharmaceuticals can we develop to treat any type of cancer or problematic site in the body? And the answer is pretty much anything, right? Anything goes. Any type of pharmaceuticals that we can put a radioactive molecule on can be used to treat problematic sites if that pharmaceutical will be taken up more by the problematic site than by organs at risk or naturally or healthy tissue. So one thing that is being looked into is antibodies. Antibodies naturally go find problems in the body, problematic cells. So if you make it radioactive, you've kind of got a double weapon on your hands, right? Which is great. Antibodies are very big particles. They take a long time to get to the problematic sites. So you need to adjust your radioisotope. If you use a radioisotope, so a radioactive particle that has too short of a half-life, and you put it on an antibody that takes 3 days to get to the problematic site in your body, you're not going to deliver an optimal dose. So you want to use a radionuclide on the antibody that has a longer half-life. But then there's a whole bunch of other things we can tag. Peptides are one that are getting a lot of action these days, or a lot of research around them. So peptides are basically amino acid chains. There's a whole bunch of different flavors of peptides, and essentially all of our cells on our body have peptide receptors to go get these building blocks. So if you find that a certain kind of tumor overexpresses a peptide receptor, then great, make that peptide radioactive, and it's naturally going to get taken up more by the tumor than by the healthy tissue. And again, you can go attack that cancerous site. But it can also be proteins. It could be pretty much anything. There's this one protein, FAP, fibroblast activated protein, that's all the rage right now. And it looks like, much like in chemotherapy, it looks like that protein is taken up by active cancer. It's taken up to in any tissue that's growing rapidly. So again, much like chemotherapy, the idea would be that cancers tend to be metastatic cancers tend to be growing rapidly. So if you can go use that process to go bring radiation into that type of tissue, then you can deliver a large radiation dose in your cancerous cells that are reproducing quickly. So all this to say, there's tons of different types of pharmaceuticals that you can use to go get a specific type of cancer. And there's a lot of research going into identifying what those types of particles are. And then, all you need to do is tie a radioactive particle on it, and you've got yourself a treatment for a type of cancer. So again, you have to think about, the chemistry and the biology here of, well, how long is it going to take to get to my cancer site? How stable is that molecule? And then also, once it's on the cell, is it going to get broken up and used really quickly, or is it going to sit there for a long time? And that can actually be engineered, right? You can engineer your peptide to not break down as soon as it gets to the cell. And that's a bit out of the hands of the physicists, but thank goodness there's other scientists out there that can kind of work on those molecules and optimize them for these types of treatments. On the physics side, though, what do we tag these things with, right? And that's where the physics and the dosimetry gets really interesting. So we know that there's different types of radioactive particles, some that emit alpha, beta particles, some that are more gamma emitters or more heavily gamma emitters, and then there are Auger electrons that can come out of decays. And all of these things can be used to treat cancers. At the base, you'd think alpha particles would be the best, right? Alpha particles deliver a large amount of energy very close to where they were, to where the decay occurred, right? They're doubly charged, very energetic when they leave, and so they're going to give a lot of dose very close to to where the decay occurred, which is great. So there's a lot of kind of excitement over alpha emitters, but there's also problems too, right? You need a very homogeneous distribution of these alpha emitters to get a very homogeneous distribution of dose throughout your tumor. So if your tumor site takes up the alpha emitting radionuclide heterogeneously, then you're not going to get a nice distribution of dose. You're just going to get hot pockets of destruction, and then other sites are going to be almost untouched, right? The range of these alpha emitters is very small. But on the other hand, you're going to get very low toxicity to neighboring tissues. So, you know, there's good and bad. The other problem with alpha particles is that they're very heavy particles. Chemically, they're just, you need to be heavier than lead to possibly be an alpha emitter. So they tend to be much harder to produce. There's very few that would be produced, for example, in a cyclotron. You'd mostly need nuclear reactors to produce these things, which is quite expensive, harder to get to, it's harder to produce, and linking them to pharmaceuticals can get trickier as well. You know, they're not as naturally a part of a peptide ring or things like that. So you need to attach them to another part of a molecule. So they're harder to produce, they're harder to put onto a pharmaceutical, which makes them more expensive, which makes them harder to deal with in general. So there's research going into alpha emitters because they do have a lot of potential, but the main emitters are beta emitters that are being looked into. So beta particles have a bit of a longer range, which is good for heterogeneous uptake of the radiopharmaceutical. It'll kind of spread the dose onto all of the organ. But it also means that there's going to be more toxicity outside of your tumor. So if your tumor is right up against the bone marrow or another sensitive part of the body, there's going to be issues there. Then you also have Auger electrons. So you've got an electron capture. It creates a vacancy in a suborbit, and then you've got these other electrons that come down and that liberate Auger electrons. Auger electrons aren't as energetic, but you can often get a cascade of them being ejected from a radioactive nucleus. So they could be interesting too. There is some action around Auger emitters. Because they're less energetic, they're again not going to have a very long range, which is great for localizing the dose to very close to where that radioactive particle was. But again, not as energetic, so not necessarily the most interesting or researched of the emitters. But you can see that there's different things in our arsenal, and you know, ideally you can project yourself down the line with infinite capabilities, and you can see that perhaps we can tweak our pharmaceuticals so to go get the best of all worlds, right? Give a bit of alpha for the first 2 cycles, for example, and then give some beta to round it off. You know, there'd be ways to optimize this, but we're not anywhere close to that as it stands now, and maybe we'll never be. So just to give you a few examples of the radiopharmaceuticals that are being talked about a lot and that are being researched quite a bit. As I mentioned, the alpha list is not as long as the beta. Radium-223 is there, so we use it at the SHRM, and I'm sure here at the MUHC since forever, just as a kind of a basic salt. But if you can tie it on to any type of pharmaceutical, it can be used much differently, right? It can, if it's tied to something that's not a bone seeker, it's not naturally going to go to the bone. That rest of the pharmaceutical is going to direct it towards the right site in the body. Actinium-225 is probably the main alpha that we hear about. We've got a clinical trial at the SHRM that is using actinium as the radionuclide that's putting in the dose, but unfortunately it doesn't emit a gamma ray, And so you can't see actinium. You don't know where it is in the body once you've injected it in the body. No information from actinium comes out. But I'll talk a bit about that a little bit later. So the beta particles are the main ones that we're really focusing on these days when we talk about novel treatments in nuclear medicine. And actually lutetium-177 is kind of the main one that everybody's talking about. So much so that we're now at a shortage of lutetium. Everybody's trying to treat with it and put it on all of these pharmaceuticals. So it's the whole system is under strain, and we're having trouble producing enough. Luckily, people are finding new ways to make lutetium all the time as well. So I think one of the facilities in Hamilton, the nuclear reactor in Hamilton, can now produce lutetium, and I think maybe Bruce Power as well. So there's, every week there's somebody new that figures out how to make lutetium, and we're really catching up, but it's being used like crazy. Iodine-131 is interesting to be on this list, right? Because we've been using it since the 40s to treat, and now more and more it's being tied on to pharmaceuticals to go treat other types of sites. What's great with iodine is that we also use it in imaging all the time. So, iodine-131 is used diagnostically to look at what's going on in people's thyroids. And, if you see that iodine is really taken up at the right places in the body, then you just boost the activity that you give to your patient, and you know that you're going to give a good radiation dose to all those sites that took it up. And that's exactly what I'm going to be talking about in the next few slides. That's the whole idea behind these new types of treatments in nuclear medicine. Just to go over a few of these other ones, I didn't translate the slide, I'm noticing now. Copper-67 is one that's getting more interest, so it's a beta emitter. But what's interesting about copper-67 is that more and more they're producing copper-64, which is a positron emitter. So copper-64 and copper-67 chemically are identical. They're both copper, which means that they can go on the exact same pharmaceuticals in the exact same way. But one of them emits a positron, so takes nice PET-CT images, and then the other one emits a beta, and so can treat. So having these pairs of atoms of radioisotopes that are of the same flavor that can be swapped for imaging and then for treatment is key. And that's exactly what I'm going to be talking about for the idea behind Theranostics. So to introduce, a buzzword, because everybody loves buzzwords, Theranostics or Theragnostics, there's debates in the field on how this should be spelt, is basically mixing or bringing together diagnostics and therapy synergistically, to put in another buzzword. So the idea is that you can take a pre-treatment image, whether it be SPECT or PET-CT, and then use that image to optimize your treatment. Right? So the idea would be that if you've got the exact same pharmaceutical, so I was talking about copper, for example, copper-64 and copper-67, you take a PET-CT image with copper-64, and you can see exactly where the pharmaceutical is going to go in the body. So you have that activity distribution, and it's even overlaid on your CT. So you can use that to then, for example, do a Monte Carlo simulation that says, well, okay, well, if this copper-64 PET-CT was distributed everywhere over the body in all of these organs, if I swap that and had put copper-67 instead, a beta emitter, where would the dose deposition have gone? So you could do a Monte Carlo calculation to show where the dose is deposited, and you can even use that, in theory, to boost your activity or lower your activity to find that sweet spot where your tumor is getting the maximum amount of dose and your organs at risk are still being shielded or still getting a reasonable dose, right? So then using this whole diagnostic image, you can find the perfect amount of activity to give in your therapy, and then in therapy you'd be using the same pharmaceutical with a different isotope on it to deliver that dose to that patient. As we'll see later too, a lot of these pharmaceuticals, or a lot of these isotopes that you're using in therapy will also emit a gamma ray. So you can even take images post-treatment to make sure it went to the right place and possibly adjust your next treatment, because a lot of these treatments are in cycles. So you can take post-treatment images and make sure everything is great for your following cycle, or tweak it to be even better next time. So, you know, that last slide was very theoretical, right? Like it was very ideal, but we'll see how it's actually done in practice. So one of the things is that, you know, there are differences between your diagnostic image and your treatment, one of them being timescales, right? So your copper-64, you're giving your pharmaceutical maybe an hour to get to the right place in the body, and you're taking a 20-minute image, whereas your treatment will be with a isotope that has, say, a half-life of multiple days. And so you're going to be giving that activity over multiple days. So is the pharmaceutical going to stay there for as long? Things like that. Like, it's not as easy as I made it out to be on the last slide. There's a lot more things to consider. So I'll just look at a few examples of these types of treatments that are being done more and more in the field. So one of the main ones that is talked about quite a bit is neuroendocrine tumors. So neuroendocrine tumors can be anywhere in the body. They come in different types. So a lot of these types of tumors happen to have an overexpression of stomatostatin receptors. So stomatostatin is a peptide. So I talked about peptides earlier. It's just a amino acid chain. And we being the scientific community, has found that these tumors overexpress the receptor. So great, let's use that information. So we can make stomatostatin, or an analog of stomatostatin, radioactive, and then you know that it's going to be taken up more by the tumor than by other healthy tissues. It's still going to go elsewhere. You still need to make sure that you don't overexpose healthy tissues, but you know that preferentially it's going to be taken up more by the tumor. So this is called peptide receptor radionuclide therapy, PRRT, and you see that PRRT coming up more and more in literature. And actually, we've been diagnosing these neuroendocrine tumors for a very long time in nuclear medicine. So we've already got the right pharmaceuticals in our arsenal, that we've been using them for years. So for example, Octrio scans with indium-111 we've been using for a long time to diagnose these neuroendocrine tumors. And that's in SPECT CTs. Since less long, but still a few years now, we've been doing more of these neuroendocrine tumor diagnostic images in PET CT, which tends to have much nicer images produced. So we've got this pharmaceutical that is called dotatate. You put gallium-68 on it, and that dotatate is, again, basically like stomatostatin. It goes to these neuroendocrine tumor sites in the body. So great, you take a gallium-68 dotatate image, you see that it preferentially finds all the metastatic sites. So then just remove the gallium-68, put lutetium-177 on that exact same dotatate pharmaceutical, and you can treat your patient. You can also put yttrium-90, so there's different types of flavors. The other types of dotatate are called dotatalk. It's basically the same thing, a little bit different. So there's, you know, different types of iterations that are all being studied right now, but the idea remains that you take this diagnostic image, you change your isotope, and then you can treat. And actually, this lutetium-177 dotatate is now Health Canada approved as a clinical drug. So for a long time, it was just a research drug, but since, I want to say 2 years or a year and a half, it's been Health Canada approved. So it's probably being used quite a bit at the MUHC to treat patients. We do, I mean, it's not overly mainstream, but we probably do a few patients a week at the SHRM on Lutathera. It's a very standard treatment now, in and out, 4 cycles, and it's very fixed dose. So Lutathera is Health Canada approved for 7.4 gigabecquerels times 4, every month and a half or something. So it's very a specific treatment. So the idea here is that you take your pre-treatment images, and in practice now, what happens is you take your pre-treatment image only to show avidity, to show that, yes, you've got metastatic sites and they take up this pharmaceutical. Then you inject amino acids to saturate your kidneys so that the radioactive peptides you put in are just going to go right through. So you protect your kidneys, and you inject the radiopeptides, so the Lutathera. And actually, that's the treatment. That's what's done. But we should be doing much more, I think. So the idea here is that pre-treatment, you should be using that pre-treatment image to quantify how much of it goes to the tumor versus organs at risk or healthy tissue. But you need to keep in mind that during your treatment, you're actually going to affect how much of it goes to the kidneys, so organs at risk. You're going to try to protect those, so you're going to change the distribution when you're treating. So you need to take that into account in your dose calculation that you did pre-treatment. And then post-treatment, this is really where things need to happen. So in clinical trials, there's dosimetry that's done. So they take images of the lutetium after 4, 24, 48, and 72 hours, typically. And then they can really see for every organ how the activity goes into the organ and comes out to do proper dosimetry calculations down the road. So you look at per organ, or for a region of an organ, or any outline, you can really see how much activity came in and for how long did it stay before biologically being ejected. And so you can make very good dosimetry measurements with that data. So this is done for clinical trials, but it's basically only done to make sure that you're not inflicting much harm. The way that a lot of these clinical trials are built is just to say, okay, so we're going to give the first 5 patients, 2 gigabecquerels for 4 cycles. If there's no adverse health effects, we're going to kick it up to 4 gigabecquerels. If there's no adverse health effects, we're going to keep going up until we start seeing adverse health effects. And the adverse health effects could be patients not handling the treatment very well, or presumably they use this dosimetry data to say, okay, at one point you've given quite a bit of dose to your kidneys, for example, or another organ at risk, and this is when we need to limit. But it's not at all patient specific, right? They use these clinical trials to say, okay, we're stopping at 7, and now the treatment is 7 gigabecquerels for everybody. Which is, it's effective in that now the Health Canada approved radiopharmaceutical can be given at any site in Canada. You don't need special facilities. You don't need much imaging time. You just give 7 gigabecquerels times 4 cycles, and that's it. But I feel like we could be doing a lot more, right? The nice thing with these treatments, which we kind of have with chemotherapy with blood tests, is that you can really quantify how well it did, even post-treatment. So at every cycle, you could be taking these dosimetry images and seeing how effective it was and using that to modulate your future cycles. Or even see, how did that patient do? Can we give him an extra 4 cycles 1 year down the road if he goes into remission, or should we be limiting how much we give to this patient? We're going in completely blind if we take no post-treatment images. So, I don't think we'll ever take a 4-hour, 24, 48, and 72-hour image on people that are not part of a clinical trial. But realistically, what I keep pushing for is at least 1 image at 24 hours so that you can get some sort of check what's going on in the different organs. And there is a bit of a push for that. Quebec City is doing a decent job at taking that data. The SHIM, unfortunately, is not. And this is my daily battle with people there. Anyway, more on that a little bit later. Another type of cancer that we try to treat regularly, or that's getting a lot of press, of course, is prostate cancer. So again, we've been doing prostate cancer diagnoses for a long time in nuclear medicine, mostly with FDG F-18 PET-CTs. So FDG is a workhorse of nuclear medicine, of PET-CTs, but it's just a sugar, right? It'll go to anything in your body that's taking up sugar, which is great, but not very refined, right? I always think of it as like killing a fly with a bazooka. Like, great, it works, but it's not elegant, which is fine. But the field right now is really growing on the chemistry side. So developing these new types of molecules that are much more specific to certain types of cells is where all of the research is going right now, and it's really exciting. And that's where we need to be focused, and I feel like physicists need to be part of that discussion as well. So for example, for prostate cancer, for quite a few years now, we've been using much more specific molecules to try to image those metastatic prostate cancers. One of them that's been getting a lot of press and that's used a lot now in diagnostics for the past few years is PSMA, so prostate-specific membrane antigen. If you put gallium-68 on it, you get nice PET-CT images. You actually can have F-18 PSMA as well. So, you know, depending on what kind of facility is around you, there's different ways of imaging PSMA. There's another one called DCF-PYL. That's, I don't know, they call it a second generation PSMA. It acts in a lot the same way, but it can target, I think often DCF-PYL can find smaller lesions a little bit better. But again, it depends a bit on the patient and on the type of cells that patient happens to have. There's choline for prostate cancers that overexpress choline kinase. So there's all these things in our arsenal. Oh, and there's also prostate cancers that are neuroendocrine in nature. So for those, you'd use the same dotatate or octrio scans that we were talking about earlier. So, you know, prostate cancer comes in all these different forms, and all of these types of molecules can be used and might be more efficient for one, or effective for one patient rather than another. So, you know, we've got like a little bit too many tools right now to try to diagnose this. But, you know, if I had 5 prostate cancer patients in front of me, again, in this ideal world where resources are infinite and radiation dose wasn't too much of a thing, we could, for all of these patients, image them with FDG, with PSMA, with DCF-PYL, with choline, with dotatate, and find which one is the best in each patient, right? So this one patient might just light up on PSMA, this other patient on dotatate, and this third patient might have 2 metastatic sites that light up on PSMA and this other one that lights up on dotatate, right? So then we can use that information to give the proper treatment, give a patient-specific treatment for that prostate cancer. And actually, you know, it sounds far-fetched in our healthcare sector, but that's actually a clinical trial that came out of Sherbrooke to do exactly that. So they were imaging cancer patients with FDG, PSMA, and octreotate and dotatate. But, and I think your site participated to that clinical trial. The SHIM did. It was a very Quebec clinical trial. So Quebec City, I think that the MUHC was on it, the Jewish, Montreal, the SHIM. And they've stopped recruiting, but I'm not sure, I don't think that the results are out yet. So essentially, it's more long-term in seeing too, like going to all this trouble to find patient-specific treatment sounds like a great idea, right? It sounds like a no-brainer, but how effective is it in reality? And I think that that's super interesting to be researching, right? We need to be looking into that to say, well, it sounds obvious that it's a good idea. Is it actually a good idea? How much does it actually help the patients versus blocking camera time for other patients that now can't get their scan? So there's a lot of debate around that, but it's important that we're looking into it. Like, our arsenal is getting so much bigger, and we need to be working with it and weeding it out and trying to find the most effective ways to be delivering this treatment to patients, right? So this is just a list of different types of pharmaceuticals that are being used. And actually, this is a list from 2019, so it's probably quadrupled since then. But it's just to give you an idea of, you know, our arsenal right now is so wide, and there's so much research going into that, but there's a lot of, again, weeding out to do and optimizing and finding the best ones. And unfortunately, as soon as you deal with the human body, you have the issue that no two people are the same, right? So something that works on one patient might not work on the other, which just complicates optimizations when you're looking at larger populations, right? So yeah, just to give you an idea, all the different compounds and then the different radionuclides that you can put on this compound, how long will that radioisotope stay on the compound versus another one? All of these things are things that need to be researched one at a time. Right? So there's a lot of action on that front, but it makes it a super exciting field. Like there's constantly new things that are coming up and promising things that come up. So where do the physicists fit in all this? It's on dosimetry, which we need to be doing, I think, more of. So what kind of dosimetry? Well, I talked about MIRD, so the MIRD standard patients. That can be used for, kind of more population or simpler forms of dosimetry. So you would go organ by organ. You can calculate, on your 3D SPECT image that you took post-treatment, for example, you can look at the activity that was deposited in whole organs, and then the MIRD kind of lookup tables will tell you, for this type of, for this energy photon and for that density tissue, and actually you have all the specific densities from your CT image, this is your dose to your organ. So those are kind of simple tools that are used, that are available, and that are being looked at. But again, there's problems of, well, your tumor is it a spherical tumor right beside an organ? That the models can deal with, but anything more complex is hard to deal with these standard humans, right? Of course, you can do full Monte Carlos on everybody. So you've got, with your PET CT or SPECT CT, you can get voxel by voxel activity distribution. So for every radionuclide that was taken up by your organ, you can do a Monte Carlo to see where the dose would be given. And that could be run, basically for every atom that was taken up. This would be long, but it would kind of be the gold standard. So there is a lot of kind of calculations and research being done on that side. But essentially, we'd look for something somewhere in between. And the field somewhere in between is huge, and it's being researched quite a bit. And actually, one of Shaheen's students that I was talking about earlier was looking into this whole something in between to optimize it and make it more numerical, make it more quantitative for these types of dosimetry calculations. So the basis is that we've got good images, right? We've got pre-treatment images that we can work with. We could get post-treatment images that really show you where the activity went. So especially if you can get it through time, you can really go make great dosimetry calculations. So the dose kernel method, essentially, you know where the activity distribution is per voxel, and the dose kernel can be seen kind of as a lookup table of, well, for every type of radiation and every type of organ, where, what kind of fuzz around that point does the dose get distributed on, and then you convolve those with your activity distribution map. So a good option for dosimetry, but at the base, you need good quantitative images. PET CTs inherently are quite quantitative. SPECT CTs are not. SPECT CTs can be quantitative, but you need good calibration and you need good quantification to be done. And this quantification will depend on the reconstruction methods, on the activity distribution, on how much activity was given, because at one point you hit dead time on your detectors. So there's a lot of physics there that needs to be looked into to really make SPECT imaging quantitative. So that's at the base what needs to be done on your machine. And then after that, you need to figure out how to best use these dosimetry tools. And the idea is to make them as simple as possible so that they can be applied all over. I think at the base, one of the problems is that drug companies want their product, and it's good. I'm not saying they're evil pharmaceutical companies. Drug companies want their products to be easily accessible to large amounts of population, right? And small centers all over the place don't have the resources necessarily to hit their heads against the wall trying to figure out how to best optimize and quantify and this and that, right? But at the same time, I'm pretty sure that giving the same amount of activity to every single patient, no matter who they are, is not optimized, right? And so if we can optimize, let's try to do it. But then you don't have the Health Canada drug. It's a lot more complicated to get to these drugs, things like that. So I think physicists need to develop simple tools, but there is a lot of dosimetry that needs to be done and that needs to be pushed forward to optimize this. And I think that that's where we need to be as a physics group to really try to optimize this whole treatment approach. And there's not, there's a few groups in Canada that are working on this, but not that much. So that's my pitch. Go into nuclear medicine. Right, so as I was saying, we need simple tools to practice personalized treatments. At what point will they be personalized? That has yet to be determined, but the field is red hot. There's tons going on. We just need to step in there and try to make this a little bit more optimal. Then the big question too is, well, do we do our dosimetry pre-treatment or post-treatment? Ideally, it's done pre-treatment, right? And so, we've got this one student at the SHIM who's working on this. Of course, if you're doing a PhD or a master's right now, you need to put in the words AI, the letters AI into your thesis. So essentially, what she's working on is exactly this idea of, well, with your pre-treatment image, you could try to run a Monte Carlo simulation to try to get the output post-treatment, or you can try to use AI, right? So if you've got all this data from previous treatments, and if you do, again, have those 4-hour, 24-hour, 48-hour, 72-hour post-treatment images, you can get really nice treatment dose maps, and you have your gallium-68 pre-treatment map. You can feed that into an AI algorithm that can then learn to output your dose map, your post-treatment dose map from your pre-treatment imaging. That would be so simple and great, but we don't have that data yet, so that's our biggest problem to get to that state. And nobody wants to take the post-treatment images because it's time, it's money, it's complicated. So there, I think that there should be more physicists in nuclear medicine. That's my conclusion. Do you have any questions? I guess I have to, thank you.